everyone. My name is Inbar Badian. I'm a senior PM in the Security CTO office of Microsoft, leading strategic initiatives from concept to execution. And unfortunately, my partner for this lecture today couldn't join us today because he's expecting a new baby, so super exciting. Yeah. So Roy couldn't join us, but he's with us. And today we're going to talk about how quantum computers are going to shake up the world of encryption. Does anyone know about the risk that quantum computers have to encryption? Raise your hand. Wow, okay. Do you know why? Okay. And do you know why now? Why should we talk about this now? Raise your hand if you know the answer. Okay, so we're going to talk about that, what the heck is quantum computer, and why it's going to affect our encryption, and what we can do already today. And first of all, I just want a disclaimer. It's not going to be a cryptography lecture. We're not going to get into the math and the technicals. We're going too much. Yeah, I know, but you have some references to read about after the lecture, and of course that we can discuss it more outside. But I just want to set the stage and make sure that we're all aligned with the basic terminology related to encryption, because we're talking about risk to encryption, so let's understand why it's so critical to understand the threats that quantum computers have on encryption and what it means. So I'm sure that you all know it, but encryption is the process of converting data as we can read it to an unreadable format. And basically, if we don't want anyone to see what we're saying, to see our secrets, we'll use encryption method using mathematical algorithms. And we're using encryption basically everywhere in our communication, in our when we're texting over WhatsApp, when we're doing payment actions. So basically, we have encryption everywhere, and without encryption, we couldn't do most of the actions involving data, and specifically sensitive data. So there are two types for encryption, and again, I'm sure that you're all familiar with this, but just to set a stage and make sure we're aligned. So let's take a look at symmetric encryption and asymmetric encryption, which are critical to this lecture. So symmetric encryption, also known as shared key encryption, it's where I want to send now an email to my colleague saying that I have chocolate in my office, but I want to say it secretly. So I'll set a key or a password, and then I'll send the email, and my colleague will have to use the same password as I said it. So this will be our shared key to exchange information securely. Asymmetric encryption, on the other hand, has two keys. Now I have the public key and I have the private key. And now if I want to send my message to the recipient, to my colleague, I will encrypt my data with the recipient's public key. And then when they want to open my message, they will use their private key. And the email software will see if the keys are correlated. And if so, if it's true, then my colleague will be able to read the message and come to my office, eat chocolate. So, two types of encryption. But now the elephant in the room, what's quantum computer, right? Who knows the answer? Okay, so we have some people who knows what's quantum computer, but let's have a deep dive. So, quantum computers are going to change the world and change humanity and everything we know today. And that's because a quantum computer is a computer that uses quantum mechanical phenomena such entanglement or superposition, which I'm sure that you all heard those terms. Superposition, for example, means that a practical can be in two states or even more in the same time, allowing those computers to perform operations on data much faster and in a much optimized way than what we can do today with our computers, with our classical computers. And not only that, the computational power of quantum computers allow them to solve some of the most hardest questions that we have today for classical computers. And those hard questions are currently the basis for everything we know about encryption. So let's understand a little more what quantum computers allows us to do, because it has so many benefits to our lives and to some of the areas that we are all affected by. So basically, quantum computers will allow us to simulate faster. If we discuss superposition, the fact that practicals can be in several states at the same time, we can now simulate more situations at the same time. So we can solve some of the more complex questions and the ambiguity that we have today around several questions that we can solve today with classical computers. Also, it will allow us to solve optimization problems. So optimization basically is to find a result, a solution, based on a set of constraints and a requested outcome. And today, optimization problems affect our business decisions, our supply chain management, and more. And in order to have those problems solved in a faster way, in a more optimized way, we are using what it calls quantum-inspired optimization, emulating the existing quantum system that we have today, to use what we got from those experiments that we already have, and to the day that we'll have strong enough quantum computers to run those experiments, we wish to have those optimization problems solved in a faster way. And also machine learning, we see how it revolutionized our lives today. So of course that if we will be able to run those algorithms on a strong enough quantum computer, we will be able to get much more information than we have today, and who knows what else we can do. It will affect chemistry, biology, the traffic jams that we have today if we solve optimization problems. Climate change depends on weather forecasting that might improve with quantum computers, and also, as we said, more knowledge and capabilities out of optimized machine learnings. So many good things, but it will also affect cryptography, for the good and for the bad. Quantum computers are going to pose a threat to asymmetric encryption. And basically, it will break everything that we know today that is based on public key encryption. For example, if we want to connect today to the internet, we're using SSL or TLS to connect to the browser, but it's based on public key encryption. And also, it's known today that most of the communication protocols that we have are based on RSA and Diffie-Hellman, which will be broken by quantum computers. And today we have two quantum algorithms that we know that can work and can break and pose a threat to our encryption by running them on quantum computer. We have Shor's algorithm related to factoring problem. And basically, Shor's algorithm running on a quantum computer will be able to find factors to larger numbers in less steps than what we can even imagine today with classic computer within a feasible time. So this will pose a huge threat to everything we know for RSA and Diffie-Hellman. The second algorithm is Grover algorithm, and I'm not going to get too deep into the explanation because we do have a solution today for Grover algorithm. Basically, Grover allows us, by running it on a quantum computer, to perform a search operation in an unordered list and find the specific items that we're looking for, posing a problem to hash. So the solution that we have today, that we can double the key or the hash size, so it's not a threat that we're looking at now, and we also have some tools, I have it in the references, that you can see what's the size of a key or a hash that is posed to the threats of quantum computers, but we're good with that. So the main problem is asymmetric encryption. And luckily, today the quantum computers that we have are too small to perform those calculations and to actually break the cryptography that we have. And usually, quantum computers today are used to academic purposes and very specific missions that we're using it. But there's a questions by tons of researchers around the world when a quantum computer will be able to break our encryption. And some of the optimistic researchers say that it's going to be in 2 or 3 years. Several say that it's going to be between 5 to 10, and others say that it's way too long. It's going to be over more than a decade. So this is a question that is here, and a lot of researchers are trying to understand this from different places. But it poses questions to everyone handling with security today. So if it's a future question, and if the threat is not today, should I care about quantum computers now? Or should I just be aware of it and, okay, it'll be good? And the answer is, we should care about this now. Because quantum attacks can happen today because there are more and more concerns that eventually there are attackers who already record the data that we have today, everything, and specifically focusing on long-term information, for example, health records or government information that is super sensitive, and also on all of our hardware and IoT devices that when implemented in the field, it will stay there even much after we'll have those quantum computers. So those attackers recorded now in wishing that when they will have a quantum computer that is strong enough, they will be able to break the encryption that we have today and read all our information. And this attack is called Harvest Now, Decrypt Later, and there's a lot of attention around it right now. So it's important to think about it even now. So post-quantum cryptography. It sounds like we don't have anything to do, right? Everyone records our data and all the information that we have, and we don't even know when quantum computers will be available. It might be next year. So what should we do? And we have a solution today, and it's post-quantum cryptography algorithms. Anyone knows what it means? Okay, I see only a few hands here. So basically, post-quantum cryptography algorithms is an emerging field. It's type of algorithms, types of encryption that designed to be resistant both to classical and to quantum computers. And basically, it was a mechanism that was known back in the past. For example, McEllis code-based crypto system, if anyone knows it. So it was designed back then, but it wasn't very popular. So everyone designed the infrastructure and IT systems to support RSA and Diffie-Hellman, which were very popular back then. And now we need to change all the encryption that we have today because we use only RSA and Diffie-Hellman and not other algorithms. So now all the algorithms that we're using may be broken by quantum computer. The PQC algorithm fall into two types. There's algorithms related to key encapsulation mechanism, related to public key encryption, what we mostly worried about in terms of the communication protocols that we have today. But we also have algorithms related to the signature, related to authentication and authenticity. Also, the common ground for all those algorithms is that they all fall into several families of hard problems. And just to make sure we're aligned on this, when I'm saying hard problems, it's the problems that we can solve today by classical computers in a feasible time. So it's just so we all be aligned on that. And those families of hard problems are currently known to be hard for quantum computers as well. So that's why it's an opportunity for us to find those algorithms coming from these families of algorithms. So we can see here lattice code, isogeny, and more. And in order to start using those PQC algorithms, we can't just start using it like that. I mean, we can, but it's not necessarily safe. So NIST, the National Institute of Standards and Technology, started a process back in 2016 to have those algorithms standardized and to make sure that we all use it, not because we want, but because we must use them as a protocol. So the process started with researchers from all across the world sending algorithms from different families. Most of the algorithms were sent based on lattice, and we'll discuss it in a minute. And there were 3 rounds. In those 3 rounds, there were several tests to test the performance, to test how to integrate those algorithms, if it's feasible, if it's not. And there were several algorithms that were broken, that were proved to be solved in a feasible time, so they were not hard anymore. And now we're started the first round with several algorithms that are currently the leading candidates, but the final round will allow us to find more algorithms from different families. As I said, most of the algorithms that we have today, as you can see here, are based on lattice. So now we're trying to diversify the algorithms that we have and to find more to make sure that we have more opportunities in case someone break the existing algorithms that we have now based on lattice. And Kyber is the leading one for encryption. Dilithium is the leading one for signature. And as we said, there were several algorithms that were broken, unfortunately. And some of them were very promising, and it was very heartbreaking to hear that they were broken. And think about that the entire process should be done by end of 2024, so we don't have enough time. And only last year, one of the leading algorithms, SIKE, was broken by 2 researchers that were able to prove that it can be solved in a feasible time. And let's get into the story of SIKE just to understand how an algorithm was actually a candidate to be a post-quantum algorithm and why it was broken. So SIKE was designed in collaboration between researchers from Microsoft, Amazon, and several universities, basically bringing everyone together, which is amazing. And this algorithm refers to a family of post-quantum algorithms that relate to Diffie-Hellman. And the idea here was to use the same approach that we have for Diffie-Hellman and to just transition it to Isogeny graph, and we'll see it in a minute, to harden the question, to harden the problem, and to make it a post-quantum algorithm. And the graph that you see here, which is horrible, that's an example of a small supersingular isogeny graph, okay? That the idea here is to find a path between 2 points and to find eventually a mutual point, which will be the secret key. And we'll see it in a minute, but you can understand why it's one of the candidates to be a hard problem. And as I said, in 2022, this algorithm that was the superhero, the Chuck Norris of the PQC algorithm was broken. And let's see why. So basically, the idea here was based on how we exchange information on top of insecure channel, which is the idea behind Diffie-Hellman. And back then, it was a question of all cryptographers in 1970 trying to understand how we can solve this question. And luckily, Diffie and Hellman found us the answer when coming up with the solution of exchanging information with the Diffie-Hellman methodology. And we'll not get into the algorithm, but just to understand how it works. Basically, each user, the sender and the recipient, choose a number, a private number. They take a public number, and again, the communication is insecure, so we have to think about a way that if we're not meeting each other physically, we can just switch a key between us. We need to find a way to have a common secret, a common way to change information. So by choosing a secret number and a public number, each of the parties, the sender and the recipient, perform calculations on the numbers again and again and sending the information until finally they find the result, which is a common number. And it's promised, based on how Diffie-Hellman works, that the final number will be the same number, which will act as the shared key. And then we're back again to symmetric encryption. So SIKE, and this is, I love this graph. It shows how the approach for Diffie-Hellman was thrown to an isogeny graph to basically, when Alice and Bob want to interact with each other, eventually they want to find a walk to a mutual point in the end, which this mutual point will act as their secret key. But as we said before, there are several calculations that we need to do in the middle and to exchange between us. So based on those calculations and the exchange of information and the metadata that we had, two mathematicians were able to break SIKE by using a mathematical theory on top of the meta points that they got from SIKE, and to show how they can solve this, find this mutual point in a feasible time. So SIKE is not relevant anymore. As you remember, we need to find problems that are not solved by either classical or quantum computer in a feasible time. So SIKE was broken, and we see more and more PQC algorithms getting broken. What can we do? And basically, I don't have a concrete answer to that, but I do have some steps that we need to take. And the first one is to remember that, as we said at the beginning, PQC is an emerging field, post-quantum cryptography. It's only in the beginning, and it's one of the hottest topics right now in security, because we all understand that we will have to transition all our cryptography to support post-quantum cryptography as well. We can't just use RSA and Diffie-Hellman as we have today. So what I suggest to do here is to explore the topic, to be aware of not just the development of quantum computers, how it's going to evolve, and what's the timeline for that, because it changes every year with the rapid development that we have, but also to track after the process of NIST, the process of the research that we have for PQC, and even be an active part of this. Researchers from all over the world are participating now to try and break the existing algorithms. So raise awareness, and not just to you, but to everyone around you, to this topic. Also, we need to remember that the crypto protocols that we have today are mainly to reduce the problems that we have analyzing complex systems. But it just brings us to a problem where we need to handle mathematical problems, which is not easy at all. But it's simpler than handling with those complex systems. But even with that, we need to remember that crypto systems need time and need people trying to break those systems again and again, and to break those algorithms, to provide us confidence that they are difficult, they can't be solved, and on top of that, we'll understand that our systems remain secure as much as possible, but we can't guarantee 100% security for our systems. And lastly, because we understand that we'll need to transition crypto, and it's not going to be the last transition, we've been through several transitions of cryptography in the past. We need to keep in mind crypto agility, and that we need to find ways to hybrid cryptography and use several algorithms at once, not just one or two algorithms that we're familiar today. And I have several resources here that you can read after, and I encourage you to read more about this topic, to be aware of it. It's a really cool topic. And let me know if you have any questions. I'll wait for you outside. Thank you so much.